Okay, so what we're doing today is this is part one of circular motion. So circular motion is higher level only. So if you're doing ordinary level, you can pretty much disregard this topic and the next topic too, topic 12, which is simple harmonic motion. Okay, so they're higher level only. Otherwise, I have part two done already because we got, with my 6 years, we got half of part one, or half circular motion done before quarantine. So I decided to just put up part one now, the first half. So just help you with revision while you're waiting for the exams to come. Okay. So the first thing here that we need to take note of is this. Okay. All along, everything has been in degrees, but now we're moving it to radians. Okay. So for circular motion, we often need the angles to be given to us the answer in radians. Right? So what you have to do, now most often they will just give it to you in radians and away you go. Okay, don't turn your calculators to radians, by the way. If you put your calculator to radians or ADS, that's what rad stands for, it won't work. You keep the calculator in degrees, but you just have to convert your angles to radians. Okay, so what is a radian? All right, so some of you might not actually know this, but what a radian is, it's when the arc length, okay, which is, let me draw it in there, this bit here. Okay, when the arc length, okay, is equal, okay, or the arc length divided by, the radius, okay, when you divide them together and they're equal to your angle, okay, as you can see down below, okay, so your arc length divided by your radius is equal to your angle, all right. In other words, 1 radian is equal to 1, all right. Or so, for example, if your arc length was 5, okay, and your radius was 5. Well, 1 radian is therefore 5 over 5. Okay? 2 radians then. Well, what would be 2 radians? Well, 2 radians would be if my radius now was 10. Okay? Your radius wouldn't change, so now the angle is equal to 10 over 5, so that's 2 radians. Okay, the angle equals 2. I should actually draw the angle in there to stop confusion. You see? So that's where it comes from. All right, so the angle in radians is the arc length divided by the radius. Okay, so when the arc length and the radius equal each other, that's 1 radian, and then when the arc length is twice the radius, 2, 3, 4, all the way around. Okay? Right. Oh, that's happening again. That's good to see. Good to see my tablet has decided to still not work properly. All right, so numerically, this is in your log tables as theta over SR. Or theta equals S over R. Sorry, not theta over SR. So theta equals S over R. Theta being the angle, arc length being S, and radius being R. Okay? So, what we're going to do here is I'm going to show you how to convert them. They're fairly easy to convert once you get the hang of it. Okay? The easiest one to remember is the first one here. 180 degrees. Okay? So 180 degrees equals pi. And I think that's in your log tables as well. Okay? 180 degrees equals pi. Remember that. That helps you answer every single one of these questions. So if you're ever asked to change it from degrees into radians, this is how you do it. Okay? So 180 equals pi. And that means 1 equals pi over 180. You see? So now you can answer every question. Every question is now answerable from this. Okay? So for example, here we have 90. So what 90 then going to be? Well, that's pi over 180 times 90. What's 45? Well, 45 would be pi over 180 times 45. What would 360 be? Well, 360, if you don't know what 360 is, just looking at it, can you think a guess before I do it? What would it be? 2 pi. Why? Well, 360 is twice 180. Okay, so what would 10 be? 10 would be pi over 180 times 10, and so forth. You get the idea. Okay? So that's how you do it. That's all you ever do. So if you're given an angle, all you do is you say, okay, how do we answer this? 180 equals pi. So therefore 180 degrees. Okay, so therefore 1 degree equals pi divided by 180. After that, you just multiply it by whatever number you're looking for. Okay, so your answers here, I'm just going to pop in the answers now. Rub all this out. Oh, I shouldn't have rubbed out that one. That one was actually fine. So that's 2 pi. So 90 degrees, obviously, if you look at it, if 180 is pi, 90 is half of 180, pi over 2. 45 is half of 90, so that's pi over 4. 360 is 2 pi. What's 10 then? So now we get out of it. So you put pi divided by 180 times 10 equals pi over 18. And we have another one, 48. Pi over 180 multiplied by 48 should give you an awkward number of 0.838. Okay? Oh, don't forget your SI unit or AD. Okay? Fairly straightforward, but again, it's good to go through it because these are the kind of things that kind of catch people out sometimes. Okay? So we move on to the next question here. Problem 2. The sun subtends an angle, that should be at an angle. The English teachers do not enjoy reading through my notes. So the angle, at an angle of 0.00932 radians to an observer on Earth. If the sun is 93 million miles away, find the approximate, because obviously with this method you can't find the exact, find the approximate diameter of the sun. Okay, so I'm assuming most of you have never seen this word before, and not going to lie, I hadn't either until when I was writing up the notes. So that's why I threw this question in, just kind of literacy, I suppose, to help you with your literacy. So what does subtends mean? It means basically if you are, so I'm going to draw on a stick man, I'm going to rub them out after. So you are on Earth, okay, all right, and the sun is 93 million miles away, okay. So subtends means that if you look at the bottom of the sun, okay, let's say imagine you're wearing sunglasses, and then you look at the bottom of the sun and somebody measures the angle at which you raise your head to look at the top of the sun, okay. So that's 93 miles, okay. The angle we make here is 0.00932 rad, and what they're asking for is what did we trace out here? What was our arc length? You see? Do you understand? So subtends, you look from the bottom of the object up to the top, and somebody tracks the angle. Okay, so you look at the bottom of the sun, and magically your eyes don't melt out of your head, and you look to the top of the sun, and you trace out an angle of 0.00932 radians. Now the sun is 93 million miles away. Okay, so we have theta. That should be theta, not whatever the hell that was. So we have theta, and we have radius, and we have now s. You see, that's how you piece this together. Okay, so I'm going to have to rub this out obviously now that I've shown that, but you can always rewind the video back because I need the space. So how do we always do with physics? Write everything down the left hand side. So we have an angle 0.00932. We have a radius which is 93 million miles. Now obviously we're not going to convert that to meters. We're just going to leave it as miles, but we have to convert it to miles from 93 million. So how do we write 93 million? That's 93, and there are 1, 2, 3, 4, 5, 6 circles. So 93 by 10 to the minus 6 miles. We leave it in miles, it's okay. And S is going to be S. Okay, so S equals S. And then all it is, what's your equation? So state your values on the left-hand side, state your equation, theta equals S over R. Make what you're looking for the subject, S equals theta over R. Sub in all your values. Oh, not sorry, that's a mistake by me. That shouldn't be theta over R, sorry. So it's theta times R. Sub in your two values. What is the arc? It is roughly 8.67 by 10 to the 5 miles. 8.67 by 10 to the 5 miles. Okay? And that's it. So always, by everything out the left hand side, state your equation. Always state your equation. You oftentimes get 3 marks. Not always, but more often than not, you will get 3 marks for that. And at the end, always state your SI units. If you won't get a mark for it, but they'll take a mark off if you don't give it. So if you left it as 8.67 by 10 to the 5, you get 2 instead of 3 marks. Simply because 8.67 by 10 to the 5 doesn't mean anything until you tell them what it means. Okay. So a particle moving in a circle. If a small particle, P, is moving at a constant speed, v meters per second, in an anti-clockwise direction, doesn't really matter, or clockwise direction. So at any instant, P is moving. All right, so this here is my P value. Okay, so it's moving this way. All right, so think back to vectors. Okay, what we have now is you have your, we call this the y-axis. So you have our y-axis vector, our vertical. Okay, that's the y-axis. But we also have our horizontal. Actually, I shouldn't call them y and x. I should call them vertical and horizontal. Yeah. Okay. So that's our vertical, and that's our horizontal. Okay. So our vertical is pulling us straight up. Our horizontal is pulling us in. So as a result, we move on the resultant vector. Okay. So for us, we're revolving around the sun, okay? So we're actually moving at a tangent to the sun. The sun is trying to pull us into it with its gravity. So as a result, we move in a vector in an orbit around the sun. That's why if the sun disappeared, we wouldn't keep moving around in a circle. We would immediately just slingshot off into space in a straight line. Same with the moon, satellites, all these things. They're actually moving around. They're actually moving at a tangent to the Earth, okay? And as a result, the Earth's gravity is pulling them into us. So if the Earth disappeared, those things wouldn't keep magically moving around in a circle. They would just start traveling in a straight line off out until, of course, another substance interacted with them, gravity from another planet or something like that. Okay? All right. So what this is, okay? I'm going to rub this out now. So because of this, all right, what happens is, what do we call this speed? Okay, well, this, because it's moving at a tangent, it says it up here, is also known as the tangential speed. Okay? But what you'll often hear being called is linear speed. Okay? So technically it's the tangential speed because it's moving at a tangent to the circle the whole time. But more often than not in the exams and in your books and in revision materials, they'll just call it linear speed. Okay? So just get used to calling it linear speed. All right? Now technically, it is always accelerating. If you remember back to equations of motion, you change direction, you actually accelerate, okay? All right? So change in direction causes acceleration. So angular velocity. This definition here, I can't remember it being asked, but know it anyway, just in case, all right? So the angular velocity is the rate of change of the angle with respect to time, okay? That's kind of, think of the name, angular, which is simply angular velocity, which is you're changing your speed, okay? But speed of what? Well, here, because it's an angle, we're changing the speed of the angle, the rate at which the angle changes with respect to time. Okay? The SI unit for this is radians per second, or rads. Note when you're writing rads, you can write it that way, or you can go or D, leave a gap, S dash. Do not go or A, D, S dash. That makes no sense. Do not do that. Leave a gap. Okay, make sure you leave a gap, a small gap, just to indicate that they're not on top of each other. What is the angular velocity symbol? It is this looking W thing here, which is actually called omega, as I mentioned here. Okay, so I know it looks like a W, but it's omega. Now, you can, if you wish, in the exams, if they ask you what is the angular velocity, you can give this. Angular velocity equals angle traced out divided by time, because it means the same thing. You can also give the equation that's in the SI unit, or that's in the log table, sorry, not the SI unit. You can give the equation, omega equals theta over t. However, if you do that, you get 3 marks. You have to then explain what does omega, theta, and t equal. So you just simply go into the notations, in other words. Omega equals angular velocity. Theta equals angle traced out. T equals time. That's it. Okay? So you have 3 options here. Okay? Personally, because I find there's a lot to learn off in general anyway, keep it simple. use the equation from the log table. Just remember to give the notation. All right, you will be asked in the exams, or not you will, you can be asked the following. All right, you'll be asked, what is the relationship between linear speed and angular velocity? Or show the relationship between linear speed or angular velocity, or prove that there is a relationship between linear speed and angular velocity. So there's any variation of this, okay? So what do they mean by that? Okay, well, simply, what we have to say is, if an object is moving in a circular path of radius r with a constant angular velocity, omega radians per second, then the constant linear speed should be v equal to r times omega. Okay, so basically it's a derivation. Derive this. Okay? With every derivation, the hardest part is where to start. Okay? You know where you need to end up. Okay? You know what we're trying to prove here. Show the relation between linear speed and angular velocity. You go to the log tables, the only equation you're going to see is this one. Okay? You go to the log tables, linear speed and angular velocity. This is what you're going to see. So you know that's the end product. You've got to get there. The problem is, where do we start? Okay? So you have to try and remember here. Okay? Is this one. Theta equals S over R. Okay? So how can I try and think? So how can you remember that? Well, try and remember what we're trying to prove here. Okay, we've got a circle. We've got an object moving at V. Okay, all right. You've got in the circle, you obviously have a radius, and you have your angle traced out. Okay, and you have your angle here, and we have R here. Sorry, not R, that should be S, sorry. You have your S here. So S is swinging around. Okay, it's moving in a circle. S is moving in a circle. I'm going to put S in red, actually, just to make S stand out a little bit more. Okay, so S is moving in a circle. Okay, S changes with the speed of V. Okay, so therefore we need to bring in the S, okay, and the R. All right, so try and think of it that way. That's the only way I could try and think of trying to make it easier for you. Okay, otherwise you're just going to have to try and remember that you start with the angle traced out. Okay, so think back. We're looking for linear speed. Well, what's the linear speed doing? Well, the linear speed is running along in a circle. Okay, we'll bring it back to the circle. What's happening in a circle? Well, if it's running around in a circle, then that means we have an arc length changing at a certain speed. Okay, well, what equation has the arc length? The arc length is theta equals S over R. Okay, that's kind of the only way I can really try and make it easier for you to remember. Okay, or maybe I just made it way more complicated. Either way, try and remember that that's where you start. Okay, so once you know that, so theta equals S over R. All right, I have written on the side here, divide both sides by T. Well, why? How would you remember to do that in the exam? Okay, well, here's the thing. We want V equals R omega. That's what we want. We want this. We have theta equals S over R. All right? Now, the first thing you should notice is that if you go to your log tables, I'm just going to roll it up here, you'll find this equation. Omega equals theta over T. You see? If we can get theta over T, we'll get rid of, see, right now we need to get rid of, we don't need theta and we don't need S. We need to get rid of them. Okay? We want V and omega. That's what we want. All right? So we're going to use this to get what we want, which is we want V and omega. All right? So when you look at your log tables, go back to the log tables, you'll find that we can get rid of theta because omega equals theta over T. All right? So omega equals theta over T, so that allows us to divide both sides by T. Now remember, why do we, some of you might ask, hopefully you don't, okay? Why do we divide both sides by T? Whatever you do to one side of an equation, you have to do to the other, okay? So if we divide the left-hand side by T, you have to divide the right-hand side by T. The reason for that is, let's say, for example, theta is 5, S is 10, and R is 2. So therefore, theta is equal to 5 is equal to 10 divided by 2. In other words, 5 equals 5. Well, if you decide, okay, well, we're going to divide the left-hand side by 5, but not the right-hand side, well, now you've created an error because now you have 1 is equal to 10 divided by 2, which doesn't make sense. Okay? 1 does not equal 5. So you have to keep, whatever you do to one side, you have to do to the other side. Okay? You have to keep it the same. All right? So we divide both sides by T. Now this, by doing this, we knock out this and we give ourselves omega. But we also do something else. We get in our V. Okay? So you end up with, all right, omega equals S over T R. All right? So now we have omega, we have R, we want to get rid of. Again, if you can't remember this, that's fine, just look at it. We have omega, that's what we want that. We have R, that's what we have that. We need V, and we don't need these two. So this sadly isn't in the log tables, you have to remember. Displacements, velocity equals displacement divided by time. V equals S over T. Dead silly triangle, distance, speed, time, similar thing. Okay? So you can knock that out and put in your V. Okay? And that's going to give you this equation here. Omega equals V over R. Okay? And then you just simply rearrange it, and that's it. Okay? How would you remember to rearrange it? Well, because you know how you want to finish it. You want it to be V equals R over omega. Or V equals R times omega, sorry. Okay? So there you go. All right? So nice and simple. Just remember what we're looking for. We're looking for the relation between linear speed and angular velocity. Go to your log tables. The equation with linear speed and angular velocity is V equals R times omega. That's what we want to finish with. So how do we start with? What is V? V is moving around in a circle. If it's moving around in a circle, it's tracing out an angle and moving around and changing the arc length. So therefore that is theta equals S over R. All right? So we have R now. We need to get rid of S and theta. How do we get rid of theta? Well, we know omega equals theta over T. Divide both sides by T. That gets rid of theta over T. S and T we need to get rid of. V equals S over T. Therefore, omega equals V over R. V equals R times omega. There you go. Okay? So practice doing that one. That one's not overly complicated. I probably gave a lot more information there than you probably needed, but I do try and explain it in a simple way that, because I have to find, guys, just learning stuff off is probably, look, some of you might prefer, but personally, it's not the best approach. You can forget it or get things mixed up. Whereas if you actually understand the maths behind it, the logic behind it, what are you doing, why are you doing it, it makes it a lot easier to remember it then in the exam, okay? All right, so problem 3 now, let me see now. So we're going to do up to date to page 5. Okay? Problem 3, sorry, I got distracted there trying to make sure I stop. So part 2, I think, as far as I know, starts at page 6. So I'll do up to page 5, and then part 2 then we'll do page 6. All right, so a small object moving in a constant speed in a circular path of radius 3 meters travels a distance of 40 meters in 2 minutes. So there's going to be 4 questions here. So part 1 is find the linear speed. Part 2, find the angular velocity. And then how long does it take for the radius of the center of the circle to the small object trace out an angle of pi over 2 rads, 60 degrees. Okay. All right. So I'm going to be rubbing stuff off constantly, but it's okay. You can always pause the video and go back. All right. So we'll start with the first part 1. Write everything out on the left-hand side, as always. So we have a radius, 3 meters. It travels a distance of 40 meters, so S, 40 meters. In 2 minutes, T equals 120. Where did I get 120 from? I can hear you asking already. Well, 2 minutes, you have to convert that to seconds. So 60 times 2 is 60 seconds in a minute. There's 2 minutes, so it's 60 times 2, 120. Okay, so the first thing up there is find the linear speed. So we're going to say V equals V. Find the angular velocity, omega equals omega. So part 1, go to your log tables, state your equation, V equals S over T. Put in your values, so that is 40 divided by 3. So V equals 0.3 continuous. Oh, I nearly said rads there for a second. I got myself confused. That is meters per second. Part 2, find the angular velocity. Again, go to the log tables. What do we have? We have omega equals T over T, and we have omega equals V over R. Oh, well, sorry, we don't have that one, actually. In the log, I rearranged that, sorry. What we have is omega equals T over T, and we have V equals R times omega. So which one should we use? I kind of gave it away there. We're going to use the second one. Why? We do not have theta, so we can't use it. So we have to use this one, okay? So therefore, omega equals V over R. V we said was 0.333, R is 3, so omega is going to be 0.111 radians per second to the minus 1. There you go. Okay? So in that one, there was two options, omega equals theta over t, or V equals R times omega. So we had to go with the second one. Why? We're missing two values here. We're missing omega and we're missing theta. Here we're only missing one, which is omega. Always pick the equation with one missing value. All right, so I'm going to update my values here before I rub them out. I want to keep track of them. 0.333, 0.111. Okay, so I'm going to rub these out now for the second, or the third and fourth part. All right, so the third part there is, how long does it take for the radius from the center of the circle to the small object to trace out an angle of theta, pi over 2 rads? I'm obsessed with theta and all that, symbols going everywhere. All right, so we want the angle to be pi over 2. All right, that's the angle. How long does it take to get that angle? So we're looking for time here. So we want t, which equals t. So what equation will give us that? What equation could we use from the log tables that has these values and not t, and so we can find t? Okay, so if you figured it out, it's omega equals theta over t. We got omega in the last part. We have got the angle, so there you go. So rearrange it, make t the subject, so t equals theta over omega. So that becomes pi over 2 divided by 0.1111. So my time, you should work out to be 14.15 seconds. Okay. Part 2, trace out an angle of 60 degrees. So what do we do here? Well, first we have to convert 60 degrees to radians. Okay, so that becomes, so theta is equal to pi over 180 times 60. Theta equals pi over 3 rad. Okay? So we have the angle again. We have omega over here, if you remember. So we put them back into the same equation. So we're going to use this equation here again. Same equation. So my time this time should work out to be 9.43 seconds. And there you go. Okay? The mistake here that a lot of people would have made, if you didn't notice, would have been forgetting to convert 60 to radians. All right. If you have any questions, guys, on any of this, please do put the comment in the comment section below or up on the Edmodo page, and I'll get back to you as quick as I can. So the next part here, this is a fairly long question, and then we'll start on centripetal force, and then we leave it at that. So this last question here, problem 4, it's a long question, so I'm going to read through the question, and I'm going to roll the screen up. You have the notes anyway, it's the top of page 4. All right, so the radius of the Earth at the equator is 6.4 by 10 to the 6 meters. What we want to find is, 1, the angular velocity of the Earth about the polar axis. 2, the linear speed of a small object at the equator. So what is the speed of an object at the equator? And 3, the linear speed of an object at 53 degrees north. All right, so I'm going to roll this up because I'm going to need all the screen. So write down on the left-hand side, what value did they give us? Okay, so they gave us the radius of the Earth. As 6.4 by 10 to the 6 meters. And that's all they gave us. Brilliant. Okay. Now in the question, they actually kind of gave you enough to answer this, obviously. All right. So the first question is find the angular velocity. So we're looking for omega. Okay. So we have the Earth here. And I'm going to draw that's the North Pole and that's the South Pole. Okay. So what it says is the angular velocity of the Earth about its polar axis, right? So what's the angular velocity about the polar axis? What that means is that the Earth spinning about the polar axis. So spinning around, okay? So what's the angular velocity of the Earth as it spins around its polar axis? Well, how long would it take the Earth to do a full circle around the North and South Pole? Can you think? How long would it take? How long does it take? You all know this answer. How long does it take the Earth to do a full circle around the North and South polar axis? And if you don't know, you're going to kick yourself in the second. 24 hours a day. It takes 1 day for us to do a full rotation around. Hence a day, 24 hours in a day. So there's 24 hours. There's 60 minutes in each hour, 60 seconds in each minute. So our time is 86,400 seconds. Okay? So we have T. We also have an angle. What angle does the Earth make as it rotates the North Pole around the South Pole? What angle does the Earth spin every 24 hours? You definitely know this one. So what angle makes it when the Earth starts at one point, spins around in a full circle back to its original point? 360 degrees, change the radians, 2 pi. So now do we have enough information to answer this question? Go to your log tables. We need angular velocity with only one missing value being the angular velocity. Well, we have omega equals theta over t. And that should give you a value of 7.27 by 10 to the minus 5 radians per second. Okay? Do you understand how I did there? They gave it away to you. They said, what's the angular velocity of the Earth about its polar axis? In other words, the Earth is spinning about the North and South Pole axis. In other words, it's doing an orbit, okay, every day. All right? So it's spinning around. All right? So it's actually an orbit's the wrong word there. Sorry, not an orbit. Apologies there. So it's doing a full spin, basically a day. Every day, the Earth spins around in a circle. Okay? So it spins around, if it's moving around in a full circle, as it spins around in 360 degrees. Okay? And the time is, of course, a day, 24 hours. Okay, so I'm going to keep the omega. I'm going to write the omega in up here now, but I'm going to have to rub everything else out because I need the space back for part 2. So we got omega to be 7.27 by 10 to the minus 5. Minus 5. Okay, so part 2 now. So that's part 1. Part 2. Right. Find the linear speed of a small object at the equator. Okay, so if we're at the equator, right, so the object is here, then we're simply dealing with the radius of the Earth, are we not? So we have the radius of the Earth, we have the linear speed, or we don't have the linear speed, we have the angular velocity, okay? And we're asked to find linear speed. So go to the log tables. Is there an equation there giving us everything and missing one equation, missing one value? So is there an equation in the log tables just missing one value? The answer is there is. V equals omega times r. We have r, it's the radius of the Earth. We have omega, it's given us in the last question. Should we still get our velocity here to be 465 meters per second? Okay, that was a little bit easier. The first part was hard. The last part is also fairly hard. Okay, so the first part was difficult. The middle part was easy enough because we have omega, we have r. We just basically find r, or find v. Sorry, not r. Okay, so I'm going to put that v value up here now because I'm going to rub that out, get space. 465. Okay, so that's part 2 done. Part 3 now is a little bit difficult. Find the linear speed of a small object at a latitude 53 degrees north. So I'm going to rub out this Earth here because I'm going to draw this a little bit bigger. Just make it easier for me to squeeze in all the information I'm going to need to squeeze in. So, alright. So that's my north-south pole axis. That's the divide. So that's north, south, east, west. Okay. What did I say? 53 degrees north. So basically we're going up here at 53. Okay. And we're asked that there's an object here. Now find its linear speed up here. Okay, find v up here. All right. How do we do it? Any ideas? Now, excuse my horrendous drawing, but this should be a proper full circle, but I don't have a compass for the computer. So imagine this is actually a proper circle. Okay, so it's not a whatever the hell that is. Okay, and so let's just pretend that's a proper circle. I don't have a compass to draw around. Okay, so we have a full circle. We've moved up 53 degrees. Well, what is this line here? This is the radius of the Earth. Okay, that's the radius of the Earth. Okay, however, that's not what we need. Okay, because we know the linear speed is v equals omega times r. Okay, v equals omega times r. The radius, okay, when you're looking at this, is going to be from here. That's the radius. We're spinning about this point. Okay, so when you're up 53 degrees north, you're spinning around the north-south axis, the radius that you're spinning at is from the radius from your point into, if you imagine an imaginary line, down through the Earth. So how are we going to answer this? What is this right now? I'm going to get a look like. What does this look like? Looks like a right angle triangle, doesn't it? And it is. Okay. It is a right angle triangle. All right. So there's two ways you can answer this question. Okay. You can either Actually, I'll just answer it my way. That won't confuse you. If you can figure out the other way, that's fine. Work away with that. Okay, so I'm going to pull this out and make the triangle here. So we have the straight line, the hypotenuse. That's the radius of the Earth. I'm just going to leave it at r. Okay, and our angle here would be 90 minus 53 degrees. We see now 90 minus 53 degrees, which is 37 degrees. So that is 37, I think. Let me see, am I right? The angle is opposite the flat bit. Yeah, so that's 37 degrees, and we're trying to find this angle down here. So that's RE. Okay, so we're trying to find the angle down on the bottom. What do we use? Sine, cos, or tan? So sine is the opposite over the hypotenuse. So sine theta equals the opposite or over the hypotenuse, the radius of the Earth. So r equals the radius of the Earth sine the angle. And that should give us, actually I didn't work that out. What I did was I just threw that in up here. So I said v, therefore, equals our omega value times the radius of the Earth sine 37. So v, you should get a v value of 280 meters per second. Okay, so for that one, you have to look at your diagram, bring it up. Okay, you have to realize you're 53 degrees north, so we're not actually spinning around the center now. So the radius has decreased. The radius to the center of the Earth is the same. Okay, it's the same to the center of the Earth, but we're not spinning about the center of the Earth anymore. We're spinning about the imaginary line going from north to south. Okay, so the linear speed at the equator is 465 meters per second. The linear speed 53 degrees north is 280 meters per second. Okay? Now, if you think about it, that makes sense. Okay? The reason being, the larger the radius, okay, the more distance you will travel to go in a 360-degree circle. The smaller the radius, the smaller the distance you go. Hence why in running and in racing or any type of racing, you always want to get the inside track, the inside lane, because when you run around the bend, you actually have a shorter distance to travel than if you're on the outside where you have a larger distance to travel. Okay? All right. So the last thing we're going to look at now is centripetal force. And I'll do the 2 questions and we leave it at that, because then you can look at part 2 to get the rest of it. So centripetal force. If a body is moving in a circle, the force towards the center needed to keep it moving in that circle is called centripetal force. Okay? If a body is moving in a circle, the acceleration it needs is called the centripetal acceleration. All right, so you need to know the 2 of them. All right, you need to know them. Could we get away with giving the equations? No, I wouldn't. Okay, you'd have to learn them off. So what is centripetal force? It is the force required to keep an object moving in a circle. Okay, all right, so it is a force. Right, so that's what you got to remember. It's the force required to keep an object moving in a circle. Now phrase the definition around that. In other words, well, if something is moving in a circle, we need a force pulling it towards the center to keep it moving that way. Okay, it is the force required to keep pulling it towards the center to keep it moving in a circle. Like, for example, the moon revolving around the earth, okay? The earth revolving around the sun, all right? What is acceleration? If a body is moving in a circle, the acceleration it has towards its center, it's a centripetal acceleration. It's pretty much the same thing, except instead of a force, it's acceleration. Your 2 equations for force then is F equals mv squared over r and F equals mr omega squared. Okay? Now, where does the omega squared come from? Well, v squared, well, we know the v equals r times omega. So v squared equals r squared omega squared. So if we sub that in, f equals m r squared omega squared over r. That r cancels that r. So you're left with f equals m r omega squared. You see? That's where it comes from. And v squared over r, well, v equals r times omega. V squared equals r squared times omega squared. So f equals mr omega squared, and so forth. Okay? And the same thing there in the bottom with the acceleration. Okay? Okay, so there are your 2 new equations. They're all in the log tables. F equals mv squared over r, or F equals mr omega squared. A equals v squared over r, or A equals r omega squared. Okay. Problem 5. A car of mass 1,200 kgs is traveling around a circular track. So keep all our information on the left hand side. M equals 1,200 kgs. That's V 25 meters per second. The radius is 200. Find the omega centripetal force. Oh, no, centripetal force. Sorry, F equals F. So, go to your log tables. Which equation do we use? We have 2 options, but only one we can use because they have all the values. mv squared over r. So our force here is therefore 3,750 newtons. Okay, problem 6. A human body can safely withstand a sustained acceleration. So A equals 9g meters per second. What that means is 9 times gravity. So 9 times 9.8 meters per second to the minus 2. G stands for gravity. What is the minimum radius which a pilot, so we're looking for r this time, if its speed is 500 meters per second. V equals 500 meters per second. Ignore gravity. Now what they mean by that is don't ignore the 9g. They mean ignore actual gravity. Okay, we're moving at 9 times the speed of gravity. So what equation can we use here? We have A, we have V, we need R. A equals V squared over R. Or therefore make R the subject, V squared over A. And that, when you put it into your calculators, should give you 2,834 meters. There you go. Okay. Right, so that's part 1 done. Part 2 is already up. I did part 2 first because my 6 years required it to get that topic finished. So this is part 1 now to catch up with it. So watch this, and if you have time, then watch part 2.